right, let's talk about this chemical equation that we've written here. This chemical equation represents the reaction that we saw with we call it the combustion of methanol. A combustion reaction, such as is represented here, is a reaction in which a carbon-containing material is burned in oxygen, so it reacts with oxygen to form carbon dioxide and water. So that's our representation here. And the chemical equation, in this sense as written, I like to sometimes think of it as a number equation. It represents the number of each type of chemical that participates in the reaction. It's not a mass equation. This is not a relationship by mass. This is a relationship by number. So there's two ways I can look at this equation. I can say, okay, 2 molecules of methanol react with 3 molecules of oxygen, and they produce 2 molecules of carbon dioxide and 4 molecules of water. Notice I'm talking about the numbers of things that react. I can also talk about moles, because a mole's a number. The chemist doesn't. So I could say 2 moles of methanol react with 3 moles of oxygen to produce 2 moles of carbon dioxide and 4 moles of water. I could talk about dozen if I want to. 2 dozen methanol molecules react with 3 dozen oxygen molecules. You get the point. All of this is a way that we can relate what happens in a chemical reaction. And so in a sense, there are some conversion factors here. So I can write, for example, 2CH3OH will react to produce 4H2O. And sometimes I'll write this little thing here like this. This means is stoichiometrically equivalent to, what in the world is that? Well, there's this word called stoichiometry. This is actually what we're studying right now, in which we think about the numbers and the masses. We'll get to that in a second, but the numbers and the masses of things that react in a chemical reaction. And I can use this as a conversion factor, and we will. There's a whole bunch of those embedded in here. I could write 2 of these is stoichiometrically equivalent to 2 of these. I could write 2 of these is stoichiometrically equivalent to 4 of these. And we'll be using those, and you should be able to see those relationships. All right, let's actually go through and show how this equation obeys the law of conservation of mass. What that means is if I start with 10 grams of this stuff, if all of it reacts and is chemically transformed, I better end up with 10 grams of this stuff over here. That's another way of what the law of conservation of mass is saying. So let's show how this is the case. Let's say I actually am starting with 2 moles of methanol. Well, how much does 2 moles of methanol weigh? We know how to do that. 2 moles of methanol. Let's see, 1 mole of methanol. How many grams is that? Well, let's figure it out. Let's go over here. Methanol, I've got 1 carbon. That's going to be 12. Look that up on the periodic table. How many hydrogens do I have? I've got 4 of them. Do you see them? That's going to be 1 times 4. How many oxygens do I have? Just 1. 1 times 16. That's going to be 32 grams of methanol is 1 mole of methanol. So if I have 2 moles of methanol, that's going to be 64 grams of the stuff, isn't it? 64 grams. Let's try the same thing with O2. Well, according to this relationship that we've figured out, it should be the case that, let's see, I've got 3 moles of O2. I want to know how many moles of O2 is, how many grams of O2 is a mole. Well, I've got 2 oxygens. That's going to be 16 times 2. I get this number by looking it up at the periodic table. That's 32 grams. So let's see. 3 times 32, that's 96. So what's that? At the start, we have 160 grams total. Isn't that correct? This plus this, that's 160 if my math is correct. What that tells me, if law of conservation of mass is obeyed, the mass of 2 moles of CO2 plus the mass of 4 moles of water, that better equal 160 grams or something. Something's not right. Let's find out. Okay, so I've got 2 moles of CO2. Let's see, 1 mole of CO2 is how many grams of CO2? I use this so much I happen to have it memorized. It's 44. Let's show you though. It's probably good to memorize that CO2 is 44 grams in a mole, but we'll do the calculation here. So I've got carbon, which is 1 times 12, because I've got 1 carbon and this is its molar mass. And then my oxygen, I've got 2 of those times 16 grams per mole. Sure enough, add them together, you got 44 grams in a mole. I gotta make sure I do this though. I gotta take that 2, there's 2 moles, multiply that by my 44. That's gonna be 88 grams of carbon dioxide. All right, now water. Water's another one I have memorized. It's 18 grams per mole. It's good to memorize water's molar mass, but we'll show you the calculation. So I've got 4 moles of water. 1 mole of water, I'm telling you, is 18 grams of water. Let's do the calculation. Go over here, and I recognize that I have 2 hydrogens and 1 oxygen. So this is 2 times 1, and this is 1 times 16. I get these numbers by looking at the periodic table, the molar mass. 2 times 1 is 2. 1 times 16 is 16. There we have it, 18 grams per mole. 4 times 18, that's 72. So this would be 72 grams. So this is 72 grams. What is 88 plus 72? It's 160. And so we've now just developed another relationship that we can use. I can say that 64 grams of methanol, if it completely combusts in oxygen, completely combusts in air, it should produce 88 grams of carbon dioxide. It should produce 72 grams of water. Now notice, we had to go through a lot of calculations to be able to get to these mass relationships. And that's important to note because you've got to remember that these chemical equations, which represent the overall reaction, those are numerical relationships. They're not mass relationships, and there's some work that needs to be done to take a chemical equation that's got a numerical relationship and convert it to mass relationships. And we're going to work through a lot of these in this particular chapter doing just this. Okay. Probably be a good idea to do the problem on slide 7 of your PowerPoint. PowerPoint 4a, stoichiometry. So this is a typical stoichiometry problem. Stoichiometry, again, meaning keeping track of how many grams of things react and how many grams of things are produced. So the problem says that we're going to put milliliters of methanol. I'm going to give you a volume. So let's say we pretend we're going to put 10 mils of methanol in that milk jug. And they give you the density of methanol. So the density of methanol is 0.78 grams for every milliliter. And we're going to assume that when we put the methanol in that jug and it reacts, all of the methanol is combusted. So all of it gets burned away. And there's a couple questions if that's the case. Well, let me write the equation first because we're certainly going to need that. So 2CH3OH plus 3O2 goes to 2 carbon dioxides and 4 waters. And the questions we want to know is, we want to know the mass of oxygen produced. Consumed, of course. Mass of O2 consumed. What is that? We want to know the mass of water produced. And we want to know the moles of CO2 produced. So 3 questions. I think I'm going to do A and B for you. Excuse me, A and C for you. I'll do A and C, and we can work out B later on. So let's try it. What is the mass of oxygen consumed? Well, here's the way I would do this. They gave us 10 milliliters of methanol. I have to convert that into a number so I can use this equation. This equation only speaks to number. It doesn't speak to volume. So what I'm going to have to do is I'm going to have to take this volume. I'm going to have to use this to convert it to a mass. And then I'm going to have to use the periodic table to get my grams to moles, my grams to number, so then I can use this equation. And then I'm going to use this equation to relate the moles of this to the moles of this. And then I'm going to use my periodic table to convert the moles of this back to the mass of this. Because ultimately what we want to know, according to the question, is what mass of this is produced. A lot of steps here. So I'll start off with my 10 mils of methanol. I'm going to use my density to convert this to grams. Let's see, 1 milliliter of methanol is going to be 0.78 grams of methanol. Okay, I've converted my mils of methanol to my grams of methanol. Next step, I need to take my grams of methanol and convert it into moles so I can use this equation. We found that was 32, do you remember? Let's do it again. Let's just do it again. So we've got carbon, that's going to be 12 times 1. We've got hydrogen, that's going to be 1 times 4. And we've got oxygen, there's one of those there, that's 1 times 16. 32 grams in a mole. So 32 grams of methanol is 1 mole of methanol. Wow. It took me 2 steps to get this into a form where I could use this equation. I'm now at the point where I can use this equation. Because what I'm trying to do is I'm trying to relate methanol to how much oxygen should get consumed. This is the key that unlocks that. For every 2 moles of this, 3 moles of this must react. That's my conversion factor. It's embedded right there in the chemical equation. So I'm going to take my 2 moles of methanol. Make sure that's right. Yep. And that's going to react with 3 moles of oxygen. We're almost home free now. For every 1 mole of O2, there happens to be 32 grams of O2. How do I know that's 32? Well, each oxygen, there's 2 of them, each oxygen is 16 grams per mole. If I figure that out by looking at the periodic table. And there we have it. We do all this math. I'm going to just make sure mils cancels mils. Mils of methanol cancels mils of methanol. Grams of methanol cancels grams of methanol. Moles of methanol cancels moles of methanol. Moles of O2 cancels moles of O2. And I've converted mils of methanol to grams of oxygen. A couple places where I see students go off the rails on this. You'll notice that I made explicit which particular compound I was talking about. So let me show you here. For example, in this step, I'll often see students write 32 grams in 1 mole. They'll just write this. And the problem with doing this is when you do this, you're all of a sudden not sure what you're talking about here. Am I talking about water? Am I talking about carbon dioxide? Am I talking about oxygen? And if you do this, I see it happen all the time. I see students lose track of what's going on and then not know what to do later. Get in the habit, as tedious as it is, go ahead and write out the grams of the compound, the milliliters of the compound, the moles of the compound related to the grams of the compound. I've been doing this 25, 30 years and I still do it to keep me from making mistakes. I still make mistakes, and this helps me avoid them. Okay, let's do the math. Let's do the math here. 10 times 0.78 divide by 32 times 3 divide by 2 times 32. 11.7 grams. So we just figured out if we burn 10 milliliters of methanol, we are going to need at least 11.7 grams of oxygen. All right, we'll do part C. It's the same starting point. If I completely burn 10 mils of methanol, how many moles of CO2 will be produced? The same process. 10 mils of methanol. I use the density. 1 mil of methanol is 0.78 grams of methanol. I'm not going to do the calculation again, but we recognize that there are 32 grams of methanol in 1 mole of methanol. This is getting me from grams to moles, so I can use this equation. In this case, I want to know moles of CO2, so I'm going to relate this to this. It's 1 to 1. It's 2 to 2, which is the same as 1 to 1, but I'll do the mathematical step here. I want to get rid of these 2 moles of methanol, and I want to convert to my moles of CO2. There, I've done it. I've converted milliliters of methanol. If it combusts, how many moles of CO2 would be produced? Let's do the math. 10 mils times 0.78 grams per mil divided by 32 grams per mole times 2 divided by 2, about 1/4 of a mole. 0.24 moles of CO2. And since carbon dioxide is 44 grams per mole, I can easily multiply this by 44 and get 10.7 grams of carbon dioxide would have been produced.